Hi there, and welcome back. We are working on problem number 2 of the homework assignment. This is a circuit with 3 resistors in parallel, and we know they're in parallel because each of their left sides, for example, touch each other. There's nothing in between, and there's no resistor, for example, in between. We know the right sides also touch each other. The right sides all touch, so they have to be in parallel. And you can kind of see that. I've redrawn it so that the lines are like this, the lines are parallel. All right. But not all lines that are parallel are a parallel circuit. You have to figure out, have to convince yourself that the left sides touch the right sides of each one. Okay, I'm not going to do it, but you should know using your equation sheet of resistors in parallel that you can use this equation, 1 over Rp, the parallel resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And remember that students often do the right-hand side, but then they forget that the left-hand side is 1 over Rp, not Rp. And again, I would use the calculator. Use the inverse button of the calculator to do that. I said I'm not going to do it, but I'm going to do it just so that we can see how I would do this. So let's see, can you see everything? So the first one is 490. So I'm going to type 490 and then hit the inverse button, which is this guy right there under the matrix. So inverse button plus 150, inverse button plus 1K, and 1K is 1,000. Okay, inverse button, boom. And so that gives me 1 over 490 plus 1 over 150 plus 1 over 1,000, and that is a small number. Anytime we work in physics, typically the physics problems will not have little tiny resistors. This is like milliohms here, 9 milliohms, 9.7 milliohms. And typically in physics, we deal with things, ohms that are resistors that are bigger than 1 ohm. So if you get a number like that, a small number for your resistance, you can have small voltages and currents, right? But typically in physics, we don't have small resistors. So what we've calculated here, this number here, is the right-hand side of our equation. So now we have to do the left-hand side. In other words, this thing over here is 1 over Rp. So a cute little trick, all you have to do is press the inverse button one more time. That's going to invert the answer, which is what we're looking for. And now that number is 103 ohms. And so that's what I've drawn there. Okay, so I lied to you and told you I wasn't going to show you, but I showed you anyway. All right, so now let's get to the problem. This hopefully is an easy step for you. Now let's get to the harder part. What is the current going through each of these resistors, and what is the voltage drop across each? In the previous problem we had resistors in series, and if you recall, the currents going through each resistor were the same. Okay, the currents going through each resistor were the same. Here, that's not going to be the case. Let's note that the battery is positive here, so we conventionally draw the current coming out this way. So this is our IN. Okay, and coincidentally, anything that comes into this junction here has got to come out of this junction. So the current going into the circuit is also the current going into the battery. All right, so when the current gets here, the current is just a bunch of electrons, right, traveling at some rate. And so where will the electrons go? Will they go up through the 490, through the 150, through the 1K? There's a saying that current follows the path of least resistance, but that's not true. I mean, it's sort of true, right? And that the least resistance, if I said most resistance, I'm sorry, current follows the path of least resistance. So the least resistance is here, the 150, but all of the electrons do not go through the 150. Some will go through the 490 and some will go through the 1K. More will go through 150 than the others, and then the second most will be the 490, and the least number of electrons will be 1,000. Yet there will be trillions of electrons that travel even through the 1,000. There will just be more that travel through the 150. All right, so that current is going to break, and I'm going to call this current here And notice that which way it goes, right? We're starting with the positive, so it's got to flow this way and got to go around this way. So I'm going to call this I490 it's associated with the 490 ohm resistor. You can call this I1 if you want to, or call it whatever you want. This current is going to be I150, and this current is going to be I1K, or I1000, whatever you prefer. I'm going to write 1000. All right, and so how do those work? All right, so we can remember that the currents in parallel add. So the currents through each resistor add up to the total current going in. So that's what we're going to use in going forward. All right, and also remember that in resistors in parallel, the voltage drops across each one is equal to each other. Each one is equal. And it's also equal to the voltage across the parallel circuit. So where's my parallel circuit? It starts here and it ends here. So the voltage drop across each of my resistors is going to be the same as the voltage drop across my battery in this case, because I can go from here straight to the battery, and I can go from here, the other side of my 490 ohm resistor, straight to the battery. I can do the same for 150, I can do the same for 150, and also for the 1000. And also, from here to here is also the same as 9 volts, okay? So before we even begin, we can look at this and we know that the voltage drop, delta V 490, the voltage drop across the 490 ohm resistor is going to equal 9 volts. And delta V 150 is going to equal 9 volts. And delta V 1000 is also going to equal 9 volts. And that's simply because we know that I just showed you. Why? Now, be really careful here, super careful. This is a pretty simple diagram, pretty simple circuit. If I had another resistor here, for example, I'm going to draw it really lightly. If I had another resistor there, then the voltage drop across each one would not be 9 volts. Okay? That's because to go from here to the battery, I would have to go through that resistor, and that's not going to give me the same voltage as 9 volts. Okay, so you have to really look carefully. Can you go all the way to the battery without going through a component? And if you can, see, I just erased it, so it's gone. So if you can, then yes, that's a potential there of 9 volts. And then back over here, this potential would be 0. So the voltage difference between there and there is 9 volts. Okay, makes sense? All right, so we've done the voltage part. That's kind of easy, right? So in one way, parallel is easier sometimes than circuit, because you can just kind of look and calculate what the voltage is. But then we have the problem with the current. How much current is going to be going through this? We can probably figure out a ratio of this to this to this, right? And that's exactly what's happening. But like, how many amps, how many milliamps is there? So what you have to do is you have to compress this big circuit, right, down to an equivalent resistance here, RP, a resistance in parallel. And again, we're going to calculate the current going through this. So this would be our IN. This would be the current going into our resistor. If we label that dot A and that dot B and kind of put this in a, oops, sorry, I'm not on the screen. And you kind of put this in a little shrouded dotted balloon or whatever, then this would be my A and this would be my B. And here would be my little dotted shrouded balloon. Okay, and so the voltage drop across this is 9 volts, and the current going into A is the same as the current going out of B. Okay, we're going to call that IN. And now we're just down to Ohm's law, which says the voltage drop is equal to RI. More specifically, the voltage drop coming into the circuit is equal to the resistance RP, the parallel resistance, equivalent resistance in parallel, times IN. And what we're looking for is IN, so let's solve for that. We know the voltage drop across this resistor, because there's nothing blocking us, there's nothing in the way, of course, is 9 volts. And RP we calculated as 103 ohms. And when you do this out, you get 0.0874 amps. Again, I'm not a fan of I lose decimals, I lose my zeros. So while we do have to work the problem in amps, sometimes it's handy to realize that this is 87.4 milliamps. It's just easier to say, easier to talk about. All right. And so now how are we going to use that idea to figure out what the current is going through each one of these? All right. So we know that the sorry, I had to clear my throat. We know that the voltage drop across each one of these is 9 volts. Okay. And so we can apply Ohm's law to each one of these as well. And let's just see what that gives us. Okay. So let me see if I can show everything here. So the voltage, we're going to use Ohm's law again for each one of these. And so we're going to use this equation that we just derived, a simple one. I is equal to delta V over R. And specifically, I for the 490 is going to equal delta V over the 490 times R of the 490. Sorry, it's hard to see. Okay. And so we know that delta V 490 was 9 volts. That's what we had right up here. Okay. And our resistor is 490 ohms. Sorry, y'all. And this gives us a current of 0.0184 amps, which is equal to 18.4 milliamps. Okay, I could do the same thing for the I-150, which is 9 volts over 150 ohms. I don't really, you can for sure. I'm not going to count off, of course. But if I've already shown what the equation is, and here we're just repeating it several times. So if you want to save a little time, I'll allow that to happen. So this is going to be 0.060 amps, which is 60 milliamps, and I of the 1000 is 9 volts over 1000 ohms. Remember, you got to convert 1K, right? 1K is 1000, so make sure that you use 1000 and not 1. And that's going to equal 0.009 amps, of course, which is 9 milliamps. Okay, so notice we didn't even have to use this current that we found in our equivalent resistance here, okay? But note that we didn't do it just for fun. We did it so that we can actually check our work. So now let's do a check. Okay, so looking at the equation sheet again, resistors in parallel, again, their current should add up to the equivalent current coming into the parallel circuitry. And so IN, which we know is this, I'm going to use milliamps here just for my check to make it easy, is going to equal to I490 plus I150 plus I1000. And lo and behold, it's 87.4 milliamps, which is exactly what we got there. And so, yay, we know we got the answer right. This solution is correct as well. All right, I'll work the next problem, which things get a lot harder, number 3 and number 4. So stay tuned for that one.